Great. So this is what we have done up until yesterday. So today we are going to discuss mainly how we handle writes. But before that, I wanted to touch into two concepts that are not fundamental. They are maybe some textbooks, maybe that many of the textbooks in computer architecture, they don't in fact cover. But I will briefly discuss them because first of all, we might have projects that cover into them. But second, it's an interesting topic to understand about because it solves some of the problems we discussed earlier for caches. These two concepts, something that's called a victim buffer or a write buffer, and the second one is called the prefetch, right? So for the victim buffer, the idea is the following. If you think about conflict messes, the way we see a conflict message, maybe I should write an example here. Let me add a slide. Okay, so assume I have an access pattern like this. Let's say A, B, C, D, and then say A again, and then D, and then B, then E again, okay? And assume I have a four-way set associative cache, and all of these are mapped to the same set, so we'll only focus on that set, right? Assume that all of them are mapped to set 0. Good. We had a similar example yesterday. What is going to happen is that I bring A first, and it turns out to be a mess. And then I bring B, and then C, and then D, all of them will turn out to be misses. Oh no, I should add another one here. That's too bad. E. Okay. Here F. Okay. So idea is the following. After I bring the first 4 lines, what is going to happen? I want to bring in E. My set is full. Yesterday we discussed replacement policies. If I'm deploying LRU, which line I should effect? So I want to bring in E from the memory, but I don't have a space. Which line I should effect if I'm deploying LRU? Yeah. A, right? Because that's the one that is least recently used, right? The one that like if you look into the time axis, the one that you didn't access for a long time, the longest is A, right? So you will evict A, remove it, and then put in E in the cache. I guess the reason that you were hesitant is because directly after I'm accessing A, right? But we said yesterday that the hardware doesn't know this. The hardware only looks at the requests that arrive to the hardware. If you were to know the future, then you would do the optimal replacement policy, but no one does this in hardware, right? So now I put in E, and then I want to bring in A back again. What is going to happen? A is going to be a mess, and then A will basically remove another line. Like in that case, it will be B, and then I will put A here, and it will be a mess. The point is, this A line, if I kept somewhere close to the cache, for example, if I had only one extra way in the set, I would have managed to hit into A, right? But the problem is that if you start increasing your number of ways, well, when do you stop? You go back to the dilemma of increasing number of ways means your T-hat will increase. So there is a trade-off here. So to address this problem, we created another smaller cache. It's a buffer, in fact. It's not a cache because it's very associative. And it's inside the cache controller itself that they call it a victim buffer or a victim cache. The reason it's called the victim buffer, you might have guessed from the name, is that if there is a line that is being evicted, which is now becoming a victim, instead of just throwing it to the lower level memory, you just put it in that victim buffer. Right? So you already freed in a space for E, but instead of just throwing in A for the lower level memory, if you put it in this victim buffer, which is close to the memory itself, what is going to happen? Later on, instead of throwing in A, and you need to go and bring it from the memory, so you suffer the high memory access latency. In this access, like if we redraw it with the victim buffer, so originally I had A, B, C, D, then I wanted to bring in E, instead of throwing A and put it in the main memory, you will put it in the victim buffer. Now, in the next access, if I have access to A again, what is going to happen? You go check your set. If it's not there, you go and check the victim buffer. If it is there, it's a very small cache. It's in fact inside the cache controller itself, so it's still a very fast access time. You take it from there and you put it back into the cache. So you saved the large miss penalty of bringing in a line that you just have recently evicted, right? And because the victim buffer is small, it only holds the lines that are evicted recently, right? Like it doesn't hold the line that has been evicted for a long time. But that makes sense. That's intuitive, because if there is a line that you evicted a while ago and you never accessed again, then most likely it has a low locality anyway, so you don't need. So the victim buffer only holds the lines that are recently evicted, because the closer you are to the eviction time, the higher probability that you might need that line again, right? Again, coming from the temporal locality concept, right? Does this make sense? Is the concept clear to you? So sometimes different architectures give this buffer different names. Like it's called the victim buffer generally, or victim cache, but also people, if this is a write, if this is an evicted line, like later on we'll see if the A is modified, and this cache only has the modified version, I cannot really just throw it away. I cannot evict it. I need to write it to the other memory, to the shared memory, because it has a modified version. This is called the write back policy. We'll discuss this later on. In that case, you place it in a buffer called write buffer, because it's waiting to be written to the memory. And the write buffer operates for writes as if it's a victim cache as well, because it holds the lines that are recently evicted, but they are dirty. They are being modified. Good. So you might see a victim buffer. For example, an Octopus simulator that you have, there is no victim buffer for reads. But I'll take this back. There is a component called write buffer, but in reality, it's a victim buffer because it holds the written lines to be written to the main memory, and it also holds the read lines that are recently evicted. So it's more like a victim buffer than a write buffer. Good. But you don't do anything with this in the lab. I'm just mentioning in case if someone is interested in the simulator, or later in the project if you pick something that is relevant. Good. Any question about a victim buffer? The main point, aside from the details, is you want to understand the inside, why it's a component that is useful and is deployed in most recent architectures. So simply, it mitigates the impact of evicting lines, right? Like instead of suffering a mess for a line that you recently evicted, you will find it in the victim buffer. Okay? Yeah. Make sense? Okay. Questions? Great. So the second concept is even more common in machines. It's called the prefetcher. And this exists starting from embedded, low-level embedded ARM architectures up to Intel and server architectures. Very, very common technique. The idea of this technique is the following. We said caches are built based on the spatial and temporal locality concept. But the only way we leverage spatial locality is when we bring in a data from the memory. We don't bring a single line. If I go back here, assume a processor requested a single line, a single byte, right? So it's a load byte something. If you're, like what we said is the cache line size in most of the machines right now. What is a normal cache line size? 64 bytes, right? So even if the processor is requesting a single line, if it's a miss in that cache, you go to the main memory and bring 64 bytes, correct? And this is how we leverage spatial locality in caches. That said, you only bring one line. You don't bring more than a line. The way the cache operates, as we said before, it operates only in a cache line granularity. If I'm a miss, I'm missing a whole line, I go to the main memory and bring it. If I'm a hit, I'm hitting in the whole line, right? But if I want to even go more aggressive and leverage spatial locality more, then I bring in more lines, right? Like because instead of accessing one line, I give you one very common example that we also mentioned before. Assume you're accessing a data structure like an array of ints, and this array is very large. If this is an array of int, so every single entry is 4 bytes, which means a cache line of 64 bytes will hold 16 entries, right? So if you go and start A0 access, it's a mess, but you bring the next 16 entries from 0 to 15, correct? And then you stop there. All of this, the first access will be a mess. All the rest will be hits. And by the way, this is something you do in the first part of the lab, like the very first question, right? You'll be able to see it. But then, after I finish the 15th, or the 16th axis, which is A of 15 here, if I go to A16, what's going to happen? Is it a mess or a head? So, well, what I'm doing right now, I'm going through a for loop through the array elements from 0 up to the array size. First one is a mess because it's a cold mess. The cache is initially empty. I bring this one, but instead of bringing one element, we bring the whole cache line. We do our math. We understand that simply a cache line holds 16 entries. So I bring 0 to 15. So once this is a mess, everything afterwards will be a hit, because the cache line has already been brought in the L1. But then once I'm done, I go to A16. Is it a mess or a hit? It's a mess because this cache line does not exist right now. So I bring in A16 and the remaining 16 elements and start being hits. But if this is a very sequential predictable pattern, which is 0, 1, 2, 3, 4, why do I need to wait until element 16 becomes a mess and then start bringing this more, right? It doesn't make sense. If I knew that simply I'm accessing it very sequentially, why I don't bring the next cache line sometime earlier, such that when I come to 16, it hits, right? And this is the main idea of a prefetcher. A prefetcher is an additional module in the cache hierarchy that looks into the access pattern, looks into the misses coming from the cache, and start learning what's happening, right? The very simple prefetcher for this very simple access pattern is bring the next line, right? Because you go completely sequential. This is called the next line prefetcher, which is a very easy case to do. If you have an access like to one line, go and bring that line, but then afterwards bring the subsequent one, right? You can imagine that this works very well in this access, but what if I have a stride? I keep jumping in my array. In that case, next line will not work, right? So we have another type of prefetcher that's called stride prefetcher. It also looks into the access pattern, look into the addresses, try to learn them, to realize that if every time I have an address, I subtract it from the previous address, I find it's a fixed stride. In that case, I know if I access address 0, and then address 4, and then address 8, what will be the pattern? 12 is afterwards, right? Because 0, 4, 8, so I jump by a 4, right? So my stride is 4. So it means if you just go to 8 and you learn that your pattern is a stride of 4, bring in 12 and then 16 and then 20. The advantage of a prefetcher is you try to bring in the data before the CPU requests it, right? By leveraging spatial locality. In that case, you try to turn misses into hits. Good. Again, as I said, a prefetcher is a very common technique in modern architectures. The way it works is that you put a prefetcher anywhere between two caches, like between the L1 and the L2, for example, or between the L2 and the LC. In reality, in all current machines, there is a prefetcher between every two levels of cache, because you want to prefetch from this cache to this cache, and you also want to prefetch from the main memory to the L2. There is a prefetcher here and a prefetcher there. Good. So the basic intuition of a prefetcher is you leverage spatial locality more than what a cache line is doing. Good. Make sense? Questions? Also, a prefetcher would be a topic for the course project if someone is interested to add a prefetcher into the cache simulator and study the impact of some of the simple prefetchers there. Currently, Octopus does not have any prefetching techniques. Great. So now, these are the two optimizations that I wanted to walk through just to complete the cache topic, give you at least hints about the terminology and what people are trying to look for. Then, one of the remaining three questions we asked last week is how do we handle writes? Because write is kind of special into how the memory should operate. And some of you already asked me questions yesterday and last week as well. The main point about a write. So what is the problem with the write? Let's first try to understand what is the problem with the write. Assume I have an L1 and I have a shared cache. Sometimes we call this LLC, which is last level cache. Let's call it an L2. And then this is L1. Now, assume the processor has a store request. Let's say first I have a load to A and then a store to A. Initially, load A will be a miss in the L1, so I go and bring in A from the L2 to the L1. Assume originally A had the value of 100, so I have 100 here. Now, assume I want to store 10 into A. One question would arise, is, should I write it here in my private cache? I'm going to be ahead. Should I write it to the shared cache? Then ignore what's happening there, right? So where to write exactly? Or should I write it in both places? Right? So where to write, this is called a write handling policy. And we have two main policies there. Something that is called write through and something that is called write back. In case of a write through, you say, because you want to keep your shared memory up to date all the time, every time you write to your private cache, go and also write to the LLC or to the L2. So you write a 10 here and you also write a 10 here. The advantage of this is this memory is up to date all the time. So if another processor, for example, requests this line, or if it happens that you evict that line, you don't need to worry about this memory because the new data is already there. So write through is good and it's easy to handle. What is the disadvantage of write through? Yeah, any idea? Yeah. Latency because? Exactly, thank you. This is like as if you are saying any write would have the latency of a miss, right? Because I write here, but I also go and write here. Right? So you have to access the slower memories all the time for writes. Right? So you create, even if it's a hit here, you didn't leverage it as much and you go and write here. It creates more memory traffic and suffers more latency. Good? This is a problem of write through. The second technique is called the write back. The idea is, if I'm having this line in my private cache, maybe I don't need to update it only once. Maybe I have something like this. Store 10 and then later on I store a 5 and then later on I store a 1. So I might issue multiple stores to the same line. If every time I go and write it to the L1 and the L2, in reality there is no point of doing this. What is important is that the L2 would have the last data update, correct? When you write back, you don't go and write to the main memory directly, but instead keep updating. So let's first visualize the write through in the figure and then we will do the write back. For write through, what I'm doing is I'm updating this to 10 and then updating this to 10. This is write through. And then I'm updating this to 5 and I'm also updating this to 5. And then updating this to 1 and then updating this to 1. This is what you do in a write through. Every time you write your higher level memory, which is L1, you write also to the lower level memory. In case of a write back, you don't do this. You say this is in fact not very efficient and it's not needed. For the load, I bring in A100 here. And then I update this 100 to be 10. Don't update L2. Then update the 10 to be 5. Then update the 5 to be 1. So you keep writing to your private cache and you keep hitting here. The advantage is you decrease the latency of writing to the shared memory. The problem is what happens if you try to evict A because of replacement. Now, if you evict A silently without doing anything, you have a wrong data in your shared cache, right? So you need to do something extra when you evict. This something extra is called the write back. You basically need to mark the lines that are being modified in your private cache, and when you evict them, you need to write them to the shared memory. You only write once when you evict. That's how it works, right? Yep. I will come into this. Yeah, because some of you might have seen a beer that write through is in fact, it's in reality the dominant technique in at least high performance architectures because it has a clear performance benefit. But there are many advantages to write through that I will come in, right? But before this, if I'm only writing this cache line to the shared memory when I evict it, how do I know whether I need to write or not? Because do I write every single line that I evict? What if I didn't even modify? It will be still very slow, right? If there is a line that you only loaded without storing, there is no point to really write to the shared memory, just really ignore, evict, right? So how to know which lines I need to write to the shared memory? Any suggestion? Yeah? Yeah, great. So you mark that line, and you would have, the way you do this is you add one extra bit, it's called the dirty bit. Previously, we had a valid bit that tells you whether the line is valid or not. Now we add one extra bit, it's called the modified bit or a dirty bit, where it's being modified from 0, like change it from 0 to 1 every time you write to a cache line. And basic right now in a replacement, what's going to happen is if your set is full, you bring in a line, you look for the candidate based on the replacement policy. If it turns out to be A, for example, before you evict it, you look into the dirty bit. If it's 1, you need to write it first to the L2 and then you evict it. Good? Oh, yeah, that's an excellent question. Thank you. In reality, yes, the common technique in most modern machines is that cache hierarchy is inclusive. Inclusive is such that anything that is in L1 is in the L2. Anything that is in the L2 is in the lower level memory, right? Yeah. There is another less common technique that's called exclusive caches. Just because the problem with inclusive caches is right now, one line exists in so many places, so it's a waste of space, right? But it's very simple to handle, it's very efficient. So yeah, that's the common technique. Yeah. So the assumption, yeah, this is what we have been assuming all the way along. Anything that is in the L1 is in the L2, and anything in the L2 is in the LLC. So yeah. Yeah, that's an excellent question, and this is the problem of coherence, right? If this question is an excellent one, but we would have a dedicated lecture for this, which is very hard to handle. The way, just to give you a hint for one statement, if there are 2 cores and this cache line is shared from one core to another, if you have something like this, and then here you have the L2 that has A equal 100, and here you would have A that originally was 100. Here you have A, which is originally 100. Assume C0 wrote 10 into it. Right now, assume, well, maybe even I didn't do this read now. Assume I want to load A. If I load it directly from the L2, I read the old bit, right? So the way this works is that there is a hardware called coherence protocol that simply says, go and broadcast this message to all the cores. If there is any core that owns a most recent version of the data, it will feed you with the data. It's more complex than this, but that's the idea how it works, right? There are some extra bits that are called coherence states that keeps handling this. Good. We will come into it. Hopefully we'll have one lecture at the end talks about that if we got the time. Good. But now the idea of write back versus write through, is that clear? So the summary is in write through, every time I write to one level of memory, I write to all the lower levels. Keep them updated. Write back, I only write when I evict. Good. If that's clear and there's no question, then comes that your friend question here is there any advantage if I throw over write back? Well, one advantage is the question related to the coherence here. If core 0 is in reality updating the shared memory all the time, this makes handling shared data pretty easy, because if the shared cache has the updated value, like for example here it would have the 10, this core can all the time read from the shared cache, right? So shared data among cores becomes way easier to handle. That's one thing. The second thing is I don't need to add this extra overhead bit of dirt. Because what do I do with it? Every time I'm writing to the shared memory anyway, so I can evict easily without worrying about whether I should write or not. You also save some overhead. And you also save some logic into the write back. So write back policy is a little bit harder to implement, right? Because you need a buffer that puts in this line that if you evict this line, I told you at the beginning of the lecture, the victim buffer. So basically, if you evict it, you put it in a buffer that's called the write buffer. It keeps in the write buffer until you write it to the shared memory, and then you remove it from that buffer. In that case, you need some extra circuitry and buffers to hold the modified data until you evict them, right? Some machines, including Intel ones and ARM ones, enables you to in fact configure from the software some bits into what they call configuration registers that turn some parts of the caches to be either write through or write back, which is I see as a very, very big advantage, right? Because in reality, for example, I'll give you one corner case where write through is not as bad as you might imagine. If I were to write only A once, like for example, I have the store A equal 10, but I don't have all the remaining stores. Would it in fact matter if I write A10 when I evict it or when I just write it? Because it's only one write anyway, I would have to pay this extra cost to write to the shared memory ones, right? So write back helps only if you keep updating multiple times before you need to evict. But if you only write once before you event, then in reality write through might be better because you just write from the beginning, your shared cache is clean, and you would pay this extra shared memory cost anyway in both cases, right? You see that it's not always one over the other. It depends on the benchmark address pattern as well. And that's why it's very good that you have the ability as a software programmer or a firmware programmer to configure the cache to be either that or that. Okay. Questions? The discussion we had here about inclusion versus exclusion is this is last point. Either your cache is inclusive, which means everything that is in the L1 is already in the LC, or it's exclusive, which means if I put a line here, for example, if this is a mess and I want to bring L2, A from L2 to the L1, I remove it from the L2 and transfer it to the L1, just to save my space, right? But this is very hard to handle. It started a decade ago, and then people faded into it. It found that it's very complex to handle, not very efficient. So inclusive cache is a common technique right now. Okay. Just for correctness, except for the last level cache in modern systems on a chip, which people call a systems cache, that is shared among CPUs, GPUs, FPGAs. This system cache, it doesn't make sense to make it inclusive at all because it really caches data that is in all different processing elements. So this one becomes exclusive, but that's a kind of a special case. I just wanted not to give you inaccurate information. Okay, so this is related to how we handle writes if I want to write into a cache line that hits into my cache. Good. There is another, maybe I should add another slide here. So the first question is where to write. And we said simply there is the write through and there is the write back. And this where to write if it was a hit, right? So basically, remember the two examples we had, A was a hit in the L1. And my question was, should I write it only in the L1 or should I write it in the LLC, right? There is another question related to write in case of a write mess, right? If you have like a store request or a store instruction, so you have an L1 here, you have the LLC. In the previous example, I intentionally made a load A first before I do the store because I wanted to bring in the line to the L1 to make it a hit. But if I start directly with the store A, which is a mess in the L1, and I want to write 10 directly into L1. Now, should I bring A to the cache and write it here, or should I just write it directly into the LLC? Two techniques are available, something that is called write allocate and something that is called non-write allocate. In case of a write allocate, the word allocate means bring it from the lower level memory to your private cache and write it there. So if this was 100, I bring it to the cache, so it's 100, and then I update it to 10. Whether you update only L1 or the LLC, this is irrelevant to this question. It's related to the question we discussed earlier, which is write back versus write through. But this question is telling you, should I fetch the data, fill it from the L2 to the L1 or not, in case of a write? If you have a write allocate policy, you bring it from the LLC to the L1. If you have a non-write allocate, in that case, you don't bring it to the L1. You have here A equal 100. You don't bring in A, but rather just write it in place. Why I might want to do this or this? What do you think? Why I might want to allocate it in the L1? An easier question. Yeah, like locality concept of a cache, because anything we mentioned earlier related to reads, here you handle writes as if they are reads. If there is an access and it's a mess, I go and bring it from the shared memory to the private memory. Hopefully later on I access it again. Right? So this is applying the locality concept as is. Right? Makes sense. But why I might not want to allocate it? Just write it in place here. Any idea? Yeah. that is correct, but what about write through? Right? So if also you have a write through, well, it saves you bring it, but then you write here and you write here, right? But there is one side in back of this is I don't bring it to the L1, which means if I access later on it would be a mess, right? That's a problem, right? In reality, one reason that why I might want to bring the write from the LLC to the L1 is that if I have a write through cache, for example, I'm writing here and I'm writing here anyway, right? So you are writing to the LLC, right? And usually people, when they study the benchmarks, they find that writes are way less than reads. Most of the time you are reading data from the memory, not writing into it. In that case, if you basically don't bring in a cache line to the L1, if you write into it, it would remain in the LLC, it would remain clean. You don't need to handle the write back delays that we mentioned earlier, just write back. And in that case, later on, if I have a read, you will bring it clean, and it will be a mess for the read for the first time, but then later on it will hit, right? So just to summarize, the case of write through versus write back, this is about write heads. The case of write allocate versus non-write allocate, this is related to a write mess. If I have a mess, should I bring it or I shouldn't bring it, right? These seem a little bit decoupled, which is true, but in reality, like one of the techniques works better with another technique. Like if you look into most modern architectures, you will find that in reality, write back, should it be more of write allocate or non-write allocate? Do you think write back, for example, will work with write allocate or non-write allocate? Based on what we explained about write back and these both techniques. What do you think? Should I have a write back cache with write allocate, or should I have a write back cache with non-write allocate? Think about how write backs really work, as we said. So in case of write back cache, you keep writing into your private cache, and you only write to the shared memory when you evac. Correct? Given this definition, which one of this is in fact working with write back? Write allocate, right? Because we keep writing to them. If I don't allocate it, I will never be able to do a write back anyway, right? Policy, because a write back policy assumes that the line exists in your private cache, correct? That's why all the write back caches are in fact write allocate. So you have something, if you open the data sheet of a processor, Intel, for example, it will tell you we are a write allocate write back cache. And this is the most common technique. Good? Then for write through, it's mostly non-write allocate, write through cache. But just to be fair, write through can work with both, right? Because write through has no implication. It can be write allocate or non-write allocate. Right? Good. But write back is the one that is requiring the write allocation, because otherwise you will not be able to keep modifying the line in the private cache. Okay. But what I'm saying right now is where two different policies play better together. It doesn't mean that they are dependent. They are really answering a different question and a different scenario. One related to the write heads, the other one is related to the write misses. Because this is, I have seen this to be a very large confusion big confusion for many even graduate students, right? These two decisions, yes, they are related because of performance reasons and some dependency, but they are really handling a different scenario, right? If I have a mess in my cache line, in my private cache for a write, then based on whether I'm write allocate or not, I bring the line to the private cache or not. After I bring it, if I have a write hit into it, should I write it only in my private cache or to the shared cache? This is a write back versus write through. Questions? This is a part that is not covered in the lab. So I want to make sure you understand it through lectures, because it's very important. It might be covered in a project, because, for example, Octopus is purely write back. It doesn't have a write through cache. And one of the open projects we have that is very manageable is to add a write through support. Right? It's easier to implement. We implemented write back because it's the harder one to implement. Okay. Yeah, we already discussed the tag reading parent versus not. It's write back, write through. Yeah, okay, so write buffer, and I guess this is the last thing we will need to discuss. If you have a write back, and I mentioned this a little bit earlier, but it's good to also look into this visualization. If I have a write back, okay, I need to explain to you these steps here. So assume this cache, we're talking about a four-way set associative cache. And then again, the same example we had earlier as A, B, C, D. And then I want to bring in E, but before this, I have E as modified. So dirty bit is 1. Okay? And assume A is the candidate for replacement. So the way that things work is the following. If E is a mess, first step, because it's a mess, as written here, you send a friend request to the next level. E is a mess, go and bring it from the next level. Step 1. In the meantime, because you know your cache is full, you try to select a candidate to free in a space until E comes in. A is your candidate. You check the dirty bit, it's modified. For that reason, you push it to the right buffer. Because you free in the set, but you know it's modified data, so you must keep until you write it to the lower level, right? So this is second step. It's called the write back buffer. Then when free comes in, when the E comes from the shared next level, you write it in the place of A, because you have already freed it in. And in the background, once you're able to issue the write from the write back to the next level, you free in the write back in. Are these steps clear? If A wasn't modified, then you don't need 2 or 4, right? Just evict it silently. You have a mess for E. You go bring it. It comes back from the shared data. Remove A and put it E here. A question to you. If A was modified, but we had a write through cache, what do I do? Yep. So which steps I can cancel then? 2. Okay. What about 4? Yeah, you don't need to send the updated data because this one has the updated data anyway, right? In case of write through, I also don't need that back. Is that clear? This only needed in case of write back. Yes? Yeah. It can be regardless, right? Like, it can be another cache, it can be a main memory. It wouldn't really matter. Yeah, well, we usually call it a lower level, which is another confusion of terminology. Usually higher, and this is in fact something that is currently confused also in Octopus Simulator source code. A graduate student confused that concept. So if you look into, so simply you have a CPU, you have an L1, L2, etc., etc., etc. The closer you go to the CPU, this is called upper level. Because in reality, this is your ultimate target. You want your stuff to be all the time here. We usually call this upper level, and the thing that is away from the CPU is called lower level. I know it might be confusing, and you might look into it, well, maybe upper level means I'm further from the CPU. No, but they look into the CPU as the highest point. This is how you can really get sense of this. So the CPU is the highest point. That means anything closer to the CPU is upper level, and these are lower level caches. Okay, because if you read a document or a data sheet or a paper, you might get confused with this terminology. Okay, so upper level closer to the CPU, lower level further from the CPU. Good. And just I'm telling you right now, for those that even when you do the project with the lab, Octopus has this wrong. Octopus calls like upper level is the thing that is further from the CPU, and lower level the thing that is closer to the CPU. Okay? Just to pay attention to this. Okay, other questions? So a last note related to writes, how writes are different than reads, is think from a pipeline perspective. Assume we have our 5-stage pipeline we discussed earlier. And then in the memory stage, I have a load instruction. In case of a load, if you remember our discussion for load and store, in case of a load, I go and bring something from the memory and place it in a register. So I'm waiting for a data to come from the memory, right? So in that case, the CPU needs this data, then it stores. In case of a store, on the other hand, the CPU is writing to the memory. You already have the data. You need to write it, right? So in reality, or fundamentally, you don't need anything from the memory. You're just really updating it. Right? So for that reason, writes usually, if you have an out-of-order processor, they don't store the pipeline. What happens is that most processors have something called store buffer here, closer to the pipeline itself, like here from the memory stage. It doesn't go, if it's a store, it doesn't go and write to the cache because it takes some time. If it's a mess, it takes even further time. They only put in the data in a buffer. And you say for the memory, once you are free, take your data. I don't care about you. And they continue the pipeline execution. So it's very important concept that writes don't store the pipeline. Reads does. That's why most of the cache hierarchy prioritizes reads over writes. Okay? That's why we have a store buffer here, that if I have a store instruction, write your data here and declare the store instruction done. It's called retire. It's done. And then I continue with what I'm doing. Later on, when the cache becomes free or it's a hit or something, it takes the data from here, write it to the cache, right? But all of this happening in the background while the pipeline is progressing. Okay? So writes are not very sensitive. Like they will usually deprioritize them because they push them into buffers and they declare the CPU is already done. Again, because you're not waiting for data, you're just pushing data. Okay? Great, thank you. So by this we are done. Just one last note. I know that the final exam is not in Mosaic yet. I'm working with the registrar office. Hopefully by end of today we will have it in. I will let you know this. The current tentative date is December 9th, but again I will need to confirm with them. Okay? This is something I don't select, so you can ask them if you would like. The second thing is that next week, just pay attention to this note because it's very important. This coming like this Friday, like the one just in 2 days, this Friday and next week, I will not be in lectures, in fact, because I will be traveling for a venue. So the TAs will be giving, we will use these slots, and this is also another reason why we're using the tutorial slots. We use these slots to solve problems. We will spend one lecture to solve the midterm with you, another one to solve cache problems with you, and the third one is to introduce the lab and see if there are questions. So we utilize this week basically to, well, do more exercises, right? And then when I come back, I will take more tutorials to focus more on the theory part, right? But next week, I will not be giving the tutorials, TAs will be giving it, okay? Sorry, the lectures also, and TAs will be giving it. Thank you.
I had a question about the write back and write through. يعني both technically will go to the lower level cache and update the value. It just differs when they do it. So.
And how many times?
And how many times, yes, and I think you also mentioned the multi-core example. So, يعني it's possible in different cores have different L1 caches and they all point